So today we're going to start chapter 7, section 1, and we're going to talk about angles of polygons. First thing we need to do is identify the parts of a polygon. So each segment that forms a polygon is called the side of a polygon. The common endpoints of two sides is called the vertex of a polygon. And a segment that connects any two non-consecutive vertices is called a diagonal. So in the picture here, all of the red lines are all the sides of the polygon, and the green line that's drawn in there is the diagonal of the polygon. Now, there's more diagonals in this, but it's only has one drawn in here. And in this picture, C isn't the only vertex here. We actually have vertices at B, all the capital letters. These are all the vertices. And I can also draw in more diagonals. You can draw a diagonal from each one of the vertices. So still from vertex D, I could draw in another diagonal to another non-consecutive vertex, and I can draw a diagonal over to A. All the other segments that I would draw would be going to consecutive vertices, and those would be forming sides. I could also draw diagonals coming out of another vertex. I could say I want to draw the diagonals out of vertex E. So I could draw a diagonal from E to B and E to C. Each vertex can have diagonals drawn out of it, and it just is drawn to the non-consecutive vertex. The next slide has the names of the polygons. We saw all of these names back in, I believe, chapter 1 or one of the beginning chapters. You can name a polygon by the number of sides. The table shows some of the common polygon names. So a three-sided polygon is called a triangle. Four-sided is a quadrilateral. This is what we're going to be focusing on in chapter 7, are quadrilaterals. We're going to see all of the specific types of quadrilaterals, and we're going to really go in depth into parallelograms. A five-sided is a pentagon, 6 is a hexagon, 7 is a heptagon, 8 is an octagon, 9 is a nonagon, 10 a decagon, and 12 a dodecagon. Any other polygon that we refer to, any other number will just have a number and then the letters GON. So if I were talking about a 50-sided figure, I would just put the number 50 and then a dash and then GON. Next, we're going to talk about finding the sum of the interior angles of a polygon. Now, we already have covered triangles in depth, and we know that the sum of the three angles of a triangle always adds up to be 180. So to find the sum of the interior angle measures of a convex polygon, you're going to draw all the possible diagonals from only one vertex of the polygon. This is going to create a set of triangles. The sum of the angle measures of all of the triangles will equal the sum of the angle measures of the polygon. Now, on the next slide, I'm going to teach you a formula so you don't need to do this every single time. But just to show you how the formula was developed, so the first picture is a triangle. Notice I cannot draw any diagonals there. So all of the vertices are going to be consecutive. And remember that the three angles of a triangle always add up to be 180. However, in this quadrilateral, I can draw in a diagonal, which is now creating two triangles. And again, the two triangles each measures 180. So I can either add 180 plus 180 or do 180 times 2. And the sum of the measures of a quadrilateral will always equal 360. Same thing for the other two figures down here at the bottom. Notice it created three triangles when I drew in all of the diagonals from this one vertex. So to find the sum of the angles of a pentagon, I'm going to go ahead and multiply 180 times 3. And the sum of all 5 angles of the pentagon will equal 540. I can do the same thing for the hexagon, but notice what has happened here is I've drawn in 3 diagonals, but it creates 4 triangles. And again, you would have done 4 times 180 to get that sum. But let's go ahead and take a look at what happens and how we can form a formula so we don't have to draw the figure and then draw in the diagonals. So instead, so the hexagon, after you multiply 180 times 4, it'll give you 720. We have this nice chart here, just showing you some examples of what happens when the triangles are formed. However, what's most important on this slide is the formula at the bottom, where it has n minus 2 times 180. This is going to be the formula that we will use to find the sum of the angles of any polygon. So let's test it out on a triangle. So remember, a triangle, my n value is the number of sides. So a triangle has 3 sides. So if I plug it into the formula, n minus 2 times 180, I get 3 minus 2 times 180. 3 minus 2 is 1. 1 times 180. And the 3 angles of a triangle, their sum equals 180. This will work for any polygon. Let's say we have a pentagon. So a pentagon has 5 sides. 5 minus 2 times 180. 3 times 180. And that sum of the polygon of a pentagon is 540. This slide has that same formula, but now presented as a theorem. And the theorem is called the polygon interior angles theorem. And again, it's just the formula. It's the number of sides minus 2. It's always minus 2. And then after you do that calculation, that little subtraction, and then you're going to multiply it by 180. Remember, this will give you the sum of the interior angles. And then a corollary to that theorem is called the polygon interior angle. That corollary just tells you that the sum of the measures of the interior angles of a quadrilateral is 360. Technically, you don't need to memorize that. You could still do the formula. However, you're going to see quadrilaterals so often that you're better off memorizing that all quadrilaterals, the sum of their interior angles equals 360, just like you did for the triangle. And the quadrilateral means any 4-sided figure. It doesn't necessarily have to be specifically a square or a rectangle. It's any 4-sided figure. Their sum will always be 360. So next we have 3 more definitions. And again, we've already seen these when we've been talking about the triangles. Equilateral just means all sides are congruent. Equiangular means all angles are congruent. And what's new here is the word regular, and we're going to use this quite often. And this just means that all sides and all angles are congruent. So in other words, whenever you see the word regular in front of a polygon name, like for example, a regular hexagon, this just means that all of the angles, all 6 of them in the hexagon, would have the same measure, and then all 6 sides would have the same length. So we saw this back in chapter 1. We did it a lot with the triangles. We had equilateral triangles and equiangular. Next, we're going to do some examples, and we're going to classify the polygon based on its number of sides, and then we're also going to determine, is it equilateral, equiangular, regular, or maybe nothing at all. Maybe it doesn't have any congruencies. So my first picture here, I'm going to count how many sides I have. I have 1, 2, 3, 4, 5, 6, making this a hexagon. And also notice that all 6 sides have the same congruency mark, as well as all 6 angles. So this is an equilateral, an equiangular, and because it's both, the better name is that it's a regular hexagon, because all sides are congruent and all angles are congruent. The next one, I'm going to count the sides. It has 1, 2, 3, 4 sides, making this a quadrilateral. But notice none of the sides are congruent together, all 4, and neither are the angles. So this is not equilateral, it's not equiangular, so it can't be regular. So this is just a regular, it's just a plain quadrilateral. It's not regular because there aren't congruencies here. Now later on, we're going to learn that this figure is a parallelogram. But right now, it's just a plain old quadrilateral, a 4-sided figure. The next one, again, I'm going to count the sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 sides, making this a dodecagon. And notice all sides, when I wrote down those numbers, I noticed all the sides were congruent. So this is an equilateral dodecagon. However, the angles are not all congruent. So this would only be an equilateral dodecagon because all 12 sides are congruent. Notice I've got all of these right angles, but there's only 1, 2, 3, that's outside, 3, 4, 5, 6, 7, 8, and then we have 9, 10, 11, 12. Those on the inside there are not 90 degrees, so they're not all congruent. Okay, so the next one is another theorem. It's called the polygon exterior angles theorem. And this one states that the sum of the measures of the exterior angles of a convex polygon, one at each vertex, is always 360 degrees. So the sum of the exterior angles of any polygon will always be 360. It doesn't matter if it's a triangle, a hexagon, a hundredagon. The sum of the exterior angles will always be 360. So for example, this is all the red angles here are exterior angles. And the way that you're going to form an exterior angle, let's just look at a triangle. If I have a triangle and I were to extend the sides, it will create an exterior angle. So if I extend the side in one direction, I can now create 1, 2, 3 exterior angles, angles that are outside of the polygon. And when I add up these angles, they're always going to add up to be 360, no matter what the shape is. So up above in that figure, up above in that pentagon, those 5 angles of that pentagon that are on the exterior part will always add up to be 360. Now, let's say the triangle I drew here was regular, meaning that it's equilateral and equiangular. So each angle would be 60. And notice each exterior angle, notice these are supplements. So each exterior angle here would be 120 degrees. And if you add 120 3 times, or even do 120 times 3, that will show you that the sum of those angles, 1, 2, and 3, always add up to be 360. And again, it doesn't matter what shape, what type of polygon it is, the exterior angles will always be 360. So if I said, what is the sum of the exterior measures of an octagon? What are you going to tell me? 360, good. What if I tell you it's a 50-agon? What will those exterior angles add up to be? 360. Before this, we were talking about sums. Now we're going to start talking about what each angle would measure if it's a regular polygon. So to find the measure of each interior angle in a regular polygon, this only works for regular, when all angles are congruent, what we're going to do is take the formula we memorized, the n minus 2 times 180, but then we divide that by the number of sides. So we just take it one step further, and now we're going to divide it. So let's take again the regular triangle. So let's say I told you have a regular triangle, and I want to know what each interior angle measures. I'm going to take my formula, my n minus 2 times 180 divided by n. N is 3 when it's a triangle, divided by 3. So 3 minus 2 is 1. 1 times 180, and then divide it by 3. And you get 60 degrees for each interior angle. So you just take it one step further. So let's try some examples, finding some measures. So when you're taking the test and the quiz on this chapter, you need to read carefully, because you need to read, does it want you to find the sum, or does it want you to find each individual angle? So this question wants you to find the sum. So I'm going to use my formula for the sum. Remember, it's n minus 2 times 180. Here's where I need to know how many sides are in the polygon names. So a heptagon is a 7-sided figure. So I'm going to be taking my formula, n minus 2 times 180. I'm going to take 7 minus 2, subtract, and multiply. 5 times 180, and the sum of the interior angles of a heptagon will equal 900. For part B, the exterior angles of a heptagon is going to be 360. No calculations here. You memorize that the exterior angles of any polygon will always be 360. So for the 17-agon, same formula. This time they already gave me the n value, it's 17. So 17 minus 2 times 180, 15 times 180, and that gives me 2,700. So that is part A for the interior angles, and part B, the sum of the exterior angles will always be 360 degrees. So this time, they want us to find the number of sides in a convex polygon given the sum. So I'm still using the same formula. I'm going to be doing n minus 2 times 180 and setting that equal to the sum. Now, there's two ways I can solve this. I'm going to go ahead and show you what you're probably used to. I'm going to distribute. So 180, I'm going to distribute it to the n and to the 2. I'm going to add 360. 180n is equal to 1,260. I now need to divide both sides by 180. And n equals 7. So the number of sides in my polygon are 7, making this polygon a heptagon. Now, the other way you can do this using your algebra skills is you could have divided both sides by 180 to begin with. It's whatever you're used to using from your Algebra 1 course. The other way you could have solved this is doing same formula. I'm just going to show you a different solving technique. You could divide instead of distributing both sides by 180 to begin with, and then you're left with n minus 2, and then 900 divided by 180 is 5, and then just add the 2, and n equals 7. So you can use either solving technique, whichever way your Algebra 1 teacher taught you, or whatever you're more comfortable using. Okay, so here it says, now we're trying to find each interior angle and each exterior. So the two formulas I'm going to use now are going to be n minus 2 times 180 divided by n. Remember, this gives me each interior angle measure. And then to find each exterior, I just take 360 and divide it by the number of sides. And this will give me each exterior. So let's try it. So here, also remember that once you find both of these, if you were to add these two together, they're always going to be equal to 180 together. They're supplements. So let's go ahead and try the regular quadrilateral. So I know that my n value for a quadrilateral will be 4. So I'm going to be doing 4 minus 2 times 180 divided by 4. 4 minus 2 is 2 times 180 divide by 4. So I'm going to multiply and divide, and you get 90. This is my interior angle. And then for the exterior, it's 360 divided by 4, which is the same calculation I just did. So each exterior angle is 90. Notice if you were to add them together, 90 plus 90 is 180. That's a way to check. Now the octagon. My n value is 8. 8 minus 2 times 180 divide by 8. 6 times 180 divide by 8. 6 times 180 is going to give me 1,080 divided by 8, and it's 135. Then to find the exterior, 360 divided by 8, and each exterior is 45. And now for the last example, 15 minus 2 times 180 divided by 15. 15 minus 2 is 13 times 180 divide by 15. And then here we're going to go ahead and get 2,340 divided by 15. And the interior angles will measure 156. And then 360 divided by 15 to get the exterior. And that'll be 24 degrees. Now I know this is the end of the notes, but I'm going to add one more example, and we're going to work backwards of the formula. So one example, the instructions will state, find the number of sides in a regular polygon given that each angle equals 165.6 degrees. So what I'm going to do is use my formula, n minus 2 times 180 divided by n, and that's going to give me what each angle measures, and that was my given. So I'm going to go ahead and set up n minus 2 times 180 divided by n and set that equal to 165.6. I need to multiply both sides by n to clear the fraction. So that will cancel the n. I'm now going to also distribute the 180 to the n and to the 2. And now I have 180n minus 360 equals 165n. I need to get my like terms together. So I'm going to subtract 180n. And now I have negative 360 equals negative 14.4n. Divide both sides by negative 14.4. And I find that n equals 25. So this would have been a 25 gone. So be able to find the number of sides either given the sum, like we did prior in the notes, or find the number of sides given what each interior angle or even each exterior angle, and be able to work backwards in the formulas. So that is it for the notes on section 7.1.